In 1D, we'll find the series for the antiderivative. We'll do it using the summation notation for the original series, but then we'll also take a look at doing it on a term-by-term basis. Okay, the antiderivative of this expression, where our variable is x. First, with the power rule, we'll need a bigger exponent by 1. Then if we're going backwards and taking the derivative of this antiderivative, you would do power n plus 1 on top times x minus 3 to this power minus 1, which is n. But we don't want that n plus 1 on top. But we'll cancel out with this one, but we need 1 to remain. So we'll need 2 factors of n plus 1 on the bottom. N plus 1 times n plus 1. Alright, now if we take the derivative of this expression, we will get this expression. So this is the antiderivative of that. Our indices, let's leave them exactly the same, but let's check that by looking at the term-by-term antiderivative. All right, let's begin out here with this term and make our way left quickly. All right, using the power rule, it would be x minus 3 to the 4th. But if we went and took the derivative going backwards, we'd have 4 times this to the 3rd, but we want the 4 to cancel out. And we want there to be an extra 4 on the bottom. So the derivative of this would be 4x minus 3 to the 3rd over 16, which reduces to a 4th. Moving along, we get the same things, and I want you to take note about this first term when we get there. You see, because if you just did antiderivative term by term, you might have thought that the antiderivative of 1 would just be x. But actually it should be following this pattern, and that's why I started from the right and went to the left. So there's really an x minus 3 there, so that it exactly follows this pattern. If we take the derivative of this, the derivative of this would be 1. All right, so now we can check our index. When n is 0, do we get the first term, which is just x minus 3? We have 1, x minus 3 to the 1 over 1. Yes, we do get x minus 3, which is the antiderivative of 1. So if we take the derivative of this, we get 1. And let's do a quick check of the second term. When n is equal to 1, we have minus x minus 3 squared over 2 squared. Minus x minus 3 squared over 2 squared. All right, it works, and our indices are correct. So let's move on to the interval of convergence. We call that the radius of convergence for any integral of a series or any derivative of a series remains the same at all times. And those boundaries also remain the same. So the boundaries were 2 and 4. What can change when you go from a series to its integral, or from a series to the series of its derivative, is whether or not we actually include those endpoints. So we will need to check each endpoint to see whether this series converges there. Let's begin with 2 and then 4. All right, if x is equal to 2, then 2 minus 3 is negative 1. And if x is 4, then 4 minus 3 is positive 1. Well, when we multiply negative 1 times negative 1, we add the exponents. This will always be an odd exponent, so the numerator will always be negative. We can write it this way. Now we could compare this to a p-series, where p is equal to 2, which converges. This isn't a p-series, but we'd compare it to it, and we'd expect it to converge, and it would. This is a converging series. Therefore, we want to include x equals 2. So come on up over here and put a bracket there. Now let's check when x is 4. Well, negative 1 to any power is 1. Positive 1 to any power is just 1, so we can ignore that. So we keep this in the summation expression. It causes the sum to be alternating. It didn't matter whether it alternates or not. In comparison to the p-series with p equals 2, it converges. This series clearly converges. And therefore, let's come on up over here, and we have a fully closed interval of convergence. That concludes problem number 1.